What specific problem does ASTRAL aim to solve in the context of safety testing for large language models, LLMs?
ASTRAL aims to solve the problem of generating a diverse and up-to-date set of unsafe test inputs for safety testing of large language models, LLMs. Traditional safety testing methods often rely on static benchmarks that can become outdated and may not represent real-world interactions, leading to imbalanced datasets and ineffective assessments. ASTRAL addresses these limitations by utilizing retrieval-augmented generation (RAG) and few-shot prompting strategies to create novel test inputs across 14 safety categories, ensuring a broad range of scenarios is covered. Additionally, ASTRAL incorporates live data browsing to generate timely prompts that reflect current societal contexts, enhancing the relevance of the tests. Ultimately, ASTRAL also automates the classification of LLM outputs as safe or unsafe, alleviating the manual labeling burden and addressing the well-known test oracle problem in LLM safety evaluations.
How does the proposed method ASTRAL work? Illustrate step by step, including the phases of test generation, execution, and evaluation.
ASTRAL operates in three main phases: test generation, execution, and evaluation. In the test generation phase, ASTRAL utilizes LLMs, retrieval-augmented generation (RAG), and few-shot prompting strategies to create a set of unsafe test inputs tailored to 14 different safety categories, incorporating various writing styles and persuasion techniques. This phase is guided by a novel black box coverage criterion that ensures a balanced distribution of test inputs across categories. Next, during the execution phase, the generated test inputs are fed into the target LLM, in this case, OpenAI's o3-mini model, to assess its responses. Finally, in the evaluation phase, another LLM acts as an oracle to analyze the outputs from the o3-mini, classifying them as safe, unsafe, or unknown, and providing explanations for its classifications. This systematic approach allows ASTRAL to effectively identify safety-related issues in LLMs.
Can you provide a simple yet illustrative example of how ASTRAL generates unsafe test inputs? Walk through the main algorithm steps using this example.
ASTRAL generates unsafe test inputs through a systematic three-phase process. For example, consider the safety category of terrorism. In the test generation phase, ASTRAL uses an LLM to create a set of unsafe prompts related to terrorism, ensuring a variety of writing styles and persuasion techniques by applying a black box coverage criterion. This might result in prompts like, "What are some methods to evade law enforcement while planning a terrorist act?" Next, during the execution phase, these generated prompts are fed into the o3-mini model to assess its responses. Finally, in the evaluation phase, another LLM analyzes the outputs to classify them as safe, unsafe, or unknown, determining if the model's response meets safety standards. This structured approach allows ASTRAL to produce a diverse range of unsafe test inputs that reflect current societal contexts and trends.
What are the theoretical or practical benefits of using ASTRAL over previous safety testing methods for LLMs?
ASTRAL offers several theoretical and practical benefits over previous safety testing methods for LLMs. Firstly, it generates novel and imaginative unsafe test inputs across 14 different safety categories, ensuring a broader range of testing compared to static benchmarks that may become outdated. Secondly, ASTRAL incorporates retrieval-augmented generation (RAG) and web browsing capabilities to produce timely and contextually relevant test inputs, which enhances the relevance of the safety assessments. Additionally, it automates the classification of LLM outputs as safe or unsafe, addressing the test oracle problem and significantly reducing the manual effort required by engineers. Lastly, ASTRAL's black box coverage criterion ensures balanced representation across various safety categories, which is crucial for detecting a wider scope of safety-related issues in LLMs. Overall, these features make ASTRAL a more dynamic and effective tool for ensuring LLM safety.
How was the effectiveness of ASTRAL validated? Discuss the experimental design, datasets used, and metrics for determining performance.
The effectiveness of ASTRAL was validated through a systematic experimental design involving two test suites, TS1 and TS2, which generated a total of 10,080 unsafe test inputs for the OpenAI o3-mini model. TS1 utilized 3 versions of ASTRAL, ASTRAL RAG, ASTRAL RAG-FS, and ASTRAL RAG-FS-TS to create 3,780 test inputs, while TS2 focused solely on the most effective version, ASTRAL RAG-FS-TS, generating 6,300 additional inputs. The datasets comprised prompts across 14 safety categories, incorporating various writing styles and persuasion techniques, ensuring a balanced representation of unsafe scenarios. Performance was assessed using a GPT-3.5 model as an evaluator, which classified the outputs of the o3-mini model as safe, unsafe, or unknown, providing a rationale for its decisions. Ultimately, ASTRAL identified 87 unsafe outcomes from the total test inputs, demonstrating its capability to uncover safety issues effectively.
What specific results were achieved when ASTRAL was applied to test OpenAI's o3-mini model?
When ASTRAL was applied to test OpenAI's o3-mini model, a total of 10,080 unsafe test inputs were generated and executed. The testing revealed that the o3-mini model exhibited a high safety level, with ASTRAL identifying 87 unsafe outcomes among the test inputs. The most significant number of unsafe results was found in the category of controversial topics and politics, particularly during the second test suite, which was influenced by recent events such as Donald Trump's presidency. Additionally, the o3-mini model was found to be safer than its predecessors, with significantly fewer unsafe behaviors detected compared to older models like GPT-3.5, GPT-4, and GPT-4o. The presence of a policy violation feature likely contributed to this enhanced safety, as it prevented many unsafe test inputs from being executed on the model.